In Chapter 5, we will be focusing on factoring techniques for polynomials, starting off with some very basic ones and moving on to some more advanced ones. First of all, the most important skill of all is being able to factor out the GCF from a polynomial function or equation. And basically, this is a way of saying that in a polynomial, sometimes the terms may have a common factor between them all. And when they do, we could factor them out or divide them out as a way of, sometimes we refer to it as the reverse distributive property. But basically, we would want to analyze each term of the polynomial and see if they share any factors. So like in the first example, 12x and 16, we'd want to look at each factor individually and determine, well, what common factors are there at all? Like you could say, well, 2 is a common factor or 4 or something, but we always want to determine the greatest common factor if there is one. So 6 is not, but it does appear that 4 is the largest common factor between each of the terms in that particular polynomial. Moving on to the second example, it seems as though, and how I like to do it is I like to look at first the coefficients, because you could always determine, if there's a common numerical factor, like between 3, 6, and 9, 3 would be the greatest common factor between them all. But also looking at the x terms is a second component of the factors of each of those terms. So in the first term, we've got 4x's, second term we've got 3x's, and the third term we have 2x's. And between all of those, they definitely have a common factor of x. And in this case, they each have at least 2x's. So our common factor of the variable component would be x squared. And if you want to remember a rule here, it's always going to be the lowest power amongst all of the powers, assuming that they all have x's within them. And that's how you can figure out your GCF of the variable component. So looking at the third example, it's a little bit more complicated. From the numbers, we've got 32, 48, and 72. And if you're not great with finding common factors, in a more difficult case, another technique you could resort to is actually finding the prime factorization of each of the numbers individually by making a factor tree. So like, for example, we've got 32, which would factor as 16 times 2, which would be 4 times 4, or 2 times 2 times 2 times 2, or 2 to the 5th power. And we could do that same process for the rest of the coefficients. We've got 48, which factors as 12 times 4, which would be 2 times 2 times 6 times 2, and of course 6 is 3 times 2. And then lastly, we've got 72, which factors as 12 times 6, of course, which is 3 times 2, and 6 times 2, which is 3 times 2. And basically, finding all of the prime factors of each number can help us determine, well, what is the greatest common factor. And basically, if you're trying to figure out the greatest common factor this way, you want to look at what factors are common in all three. So what I would look at first is, well, 3 was common between 48 and 72, but there was no 3 within 32. So 3 is not going to be a part of the common factor in this case. But however, 2 is definitely a common factor, and we could count the number of 2's that are common. So 72 has 3 2's, 48 has 4 2's, 32 has 5 2's, and we would use the smallest number. So in this case, it will be 8. 8 is going to be the greatest common factor of the numerical component here. And then moving on to the variables, and notice that kind of idea is very similar to how we would do it with the variables, where we, like I said, use the lowest power. If I'm looking at all the numbers, I want to know, well, what is in common and what's the lowest power of those. Sort of the same idea. And with A, well, each one has at least 2 A's. It's actually much easier to determine the common factor of the variables, even though we're not, we're more used to thinking about how to factor numbers. And then as well, same thing with b squared. So that would be the greatest common factor of each case. And now, well, we're not done. I was just trying to illustrate how we actually find the greatest common factor. But in each case, we can factor out the greatest common factor, which is another way of saying we could divide it out from the polynomial. Like in the case of 12x plus 16, and what I always recommend doing is basically you can write it out front of a parentheses and put the secondary part in parentheses. And basically we're reversing the distributive property, because since 4 is common, I could rewrite this as 4 multiplied by, well, whatever is left over after I factor out the 4, or sometimes I might say pull it out or extract the common factor. But you know, if you're not great at figuring out what should be remaining after factoring out the 4, remember that factoring something out is really a synonym to dividing. When we're undoing a multiplication, that's the same as division. So if you're better at division, you could just say, well, 12x divided by 4 is 3x, and 16 divided by 4 is 4. And then anytime you're factoring, this goes for all factoring that we're going to talk about, not just GCF. We can always check to see, does this make sense by remultiplying it out? And if I apply the distributive property to multiply this out, this would leave me with 12x plus 16. And I can see that that's indeed equal to what I had to begin with. And obviously that gets me back to where I started, which is not necessary, because when we're factoring, the goal is to take something expanded and put it in a factored form. Now, sometimes you might be asked to multiply it out, and you might be wondering, well, what's the correct answer? It's not really about a correct answer. It's just about taking a polynomial and writing it in a different way, using a factorization, as we call it. And same thing with the other two. Once you know the greatest common factor, first step is to figure out the greatest common factor, and the second step is to figure out, well, what would remain after factoring that out. So from the second example here, again, you could think about this as dividing it, but basically each term, we would need to have 3 terms within the parentheses because we're factoring out 3x squared from each one of them. But if I divide this by 3x squared, what I'd be left with is x squared. If I divide 6 by 3, that would leave me with plus 2, and x cubed by x squared would leave me with just x. And then 9x squared, 9 divided by 3 would be positive 3, and x squared over x squared would leave me with no x's. And so this would be the answer for the polynomial after factoring out the greatest common factor. And if I were to multiply this out, I would get 3x to the 4th plus 6x cubed plus 9x squared. And that is perfect. Now in the last example, looks like I didn't give myself quite enough space here. But if I were to divide each, again, you would make sure that the numbers are being divided. So 32 divided by 8 would leave me with 4. And that, if you're, you can always just subtract the exponents because that's how we divide exponential expressions. So a cubed over a squared would leave me with 1a, and b squared over b squared would cancel. Negative 48 divided by 8 would leave me with negative 6. A squared would cancel, b squared would cancel. And 72 divided by 8 would leave me with 9. A squared would cancel, b cubed divided by b squared would leave me with b to the first, or just a lone b. And again, assuming I did my dividing correct, the fact when I multiply this out, this should work. And again, we could verify that. That's always optional, but a good thing to check with your factorization, especially if you're guessing or if you're not really being very careful. So there's a couple extra practice questions in the packet for today. Go ahead and work on those and try them out yourself. In the next video, I'm going to talk about factoring by grouping. Factoring by grouping is a very important technique that we're going to be using in class this week. And I'll review it when class starts, but it's a little bit of a trickier one, and I'll make sure to go in depth on how that works.